In this Python exercise, we're going to go through the linear and logistic regression. Um, so, actually creating the models, evaluating, and starting to get into the interpretation. We're going to start off with the CARS dataset. So, I've included the same info like I did last week, just in case you wanted to look at it. But make sure you have the CARS dataset saved in your files wherever you have saved them. And then I'm going to get started. So we're importing packages. Again, we're starting off with pandas and NumPy, whichever you'd prefer, but the two main packages that we use for data analysis. And we're going to import the CARS dataset. Now I do want to start off with matplotlib. I want to show you the chart that I had in the slides. So horsepower versus miles per gallon. So that's the first one we're going to try to solve using the linear regression function. Remember that these two variables are correlated and they're negatively correlated. So as horsepower increases, miles per gallon decreases. Or in other terms, as miles per gallon increases, horsepower decreases. So we want to try to create an equation for that using linear regression. So to start off, we're going to import two libraries. First, from scikit-learn, or when we're importing, it's just sklearn, import linear regression. And we're also going to import the train test split module. So next up, we need to specify our independent and dependent variables. And then we're going to train the model by splitting our data set into training and testing sets. And honestly, I Googled linear regression in Python so that I could remember what this linear regression was called. It was just linear regression. You'll notice the code popped up automatically. You'll need to double check everything. If AI pops up with anything, you can almost guarantee something might be wrong. But it gives you a really nice start. So don't feel bad about Googling it and trying to find something. So we're going to start off. I like having everything as X and Y. This helps me just keep everything straight and I can use my code over and over without having to redo anything. So I'm going to have X, and this is a capitalized X, equals data frame horsepower. You'll notice I use two square brackets. So this, instead of basically referring to a column, this actually selects the column when I use two square brackets. So my X is going to be horsepower and my Y is going to be miles per gallon. The next part is using that train test split library. So what it's doing, it's calling this train test split, and I've sent it my new data frames that I want it to create. So I want it to create train and test data frames for X and Y. So I'm going to send it my X variable, my Y variable. I'm going to tell it my test size. So in this case, I'm telling it 0.2 or 20%, which means that 80% of my data is going to be used for training and 20% is going to be used for testing. And then I've also told it a random state. This is basically a seed variable if you've used it in R, but it's telling us, or telling Python, if I want to come back to this very specific train test split, this is the value to use. And it's because it's splitting it into random parts. And if I don't include this, it's going to split it randomly every single time, and I'm never going to have the same results. So this allows me to have the exact same results every time, and for you to have the same results when you run it in your notebook. You can use any number you want. I'm using 42. You can guess why. So X train, if I wanted to look at it, you'll notice it's horsepower. There's only 5 of them because it's the head function. And you'll notice that the index of these, so it's 25, 12, 0, that's because they were selected randomly, so they are random. And for the Y, it's miles per gallon. And it's the same index because I want them to match up, but I just want the X, so the independent variables, to be separated from the Y, the dependent variables. And now here comes the model building. So thankfully, when we're doing model building with scikit-learn in Python, it is the exact same every single time. every time we are going to define the model and its parameters. So what do we want the model to be and what parameters do we want to set? In this notebook, you'll notice we have no parameters. So we're just keeping it exactly how it is, the default. We're going to mess with the parameters next week. We're going to fit the model. So the first one just says, here's a model. The second one says, this is the model I want to use with my data. Number 3, I'm going to make the predictions. So number 2 is using the training set. Number 3 uses the test set. And number 4 goes into the evaluation. So is the model good or not? So let's try it out. When you're looking at the model parameters, I definitely want you to look at the documentation that I've put here. It'll go through all the different parameters that are built in. Again, we're going to keep it as is for now, but this is here. So I'm calling this first one just linear model so I can keep track. And you'll notice it actually doesn't do anything. And I haven't sent any data here. So all I'm doing is initiating this model. It's a linear regression model that I've called linear model, and that is it. It doesn't have my X, my Y, anything. Once I fit the data, that's where it actually gets my data. So I'm going to say linear model, take that linear model and fit my data. I'm going to send it my X and my Y data, and it's training data for both times. You don't send it your test data because those are the ones that have the answers. I don't want it to know that yet until I'm going to evaluate it. And all it did here was just say, yep, okay, I fit it. It's fitted, and you can look up some values here if you want to. Now I'm going to make predictions. So I'm going to make a new variable called y prediction. So I'm going to take my linear model, and there's a function called .predict. So I send to x test. So here's the x. So it had made this formula, the y equals a plus bx. I'm going to send to x and see what it says for y. And now I have to evaluate the model. So remember, for linear regression, you can look at r squared, you can look at mean square error, and there are actually 2 ways to look at r squared, so I'm going to show you both. The first one is just your linear model dot score, and you send to x test and y test. Oof. Okay, remember r squared, it's between 0 and 1. So this is about a 0.4, 40%, so not so good. Not horrible, but not so good. And then the other version is you can actually import a specific r squared module, but you'll see it's the exact same number. So I am going to use this one going forward. It's easier, it's built in. But yeah, 0.4 on a scale of 0 to 1, getting a 0.4 means not so great. It's I wouldn't give this to anyone and say this is the model we should be using. This is only saying that 40% of the variation in miles per gallon is explained by horsepower. So that means there's a lot I'm missing out on, whether it's random variable or random chance or other variables. We can also visualize those results. So we can look at x test, y test, and then x test and y prediction. And we'll get into this in a moment, but this is part of the problem. There's not a lot of test data left because it's a very small data set. But you see it drew the line here, and it works well for a linear regression where part of it's above the line, part of it's below, looks about evenly spread. But we've got some outliers up here, right here. It's just not a great line for this. If you calculate mean square error, it gives you 24. We want mean square error as close as possible to 0, so 24 is not fantastic. So we're probably missing some information. So if we go to multinomial linear regression, so that's multivariate. Sorry. I mean, multinomial probably works, but multivariate, let's try more variables in our regression model. I'm only going to put in numeric variables because we are looking at a numeric model. So basically all I want is everything except this model variable, if you remember. So I'm going to change x to everything but model. and y is going to stay the same as miles per gallon. And this, again, is why I did X and Y, because now I can run this, and then I just copy and pasted all of those cells from above, and I don't have to do anything else. So run this again. You can see, oops, I forgot to run that part. So this is the problem with notebooks. If you run it out of order, you run into a problem. So make sure you run it in order. There we go. That looks better. Now I can run this. I'm calling this linear model 2. And then do the same thing. And now my R-square is about 75%, which is much better. So we went from 40% variation explained to 75% by adding in a few extra variables. We are going to go over variable selection in another module, but the basics you need to know are that exploratory data analysis, that stuff we did all of last week, that was for a reason. You should know how your variables influence your dependent variable by actually looking at them, plotting them, trying out some things. There are other ways to do linear regression. So we did one variable and then we did all of the variables. There are also stepwise, forward, backward selection. So stepwise is when they start with all of the variables and then they take away one at a time. That's backward selection, backward selection. Stepwise, it starts with the one that has the best relationship with the y variable, and then it adds back one at a time until you get the best model. So there's lots of them out there. I do recommend you look into them, but for this class, we're going to stop here. Logistic regression works pretty much the same way. Again, if we start off with that miles per gallon versus transmission, you'll notice that logistic function might work pretty well here, that little kind of S shape. We need to import the logistic regression model package. And then same thing, we're going to say X is miles per gallon, and Y is, it's called VS, that's the transmission variable. We're going to split into training and testing. Create the logistic regression model. There is one thing I had to change here, and I'm actually going to take it out for a second so you can see what happened. So if I do this and I just give it X train and Y train like we did for linear regression, it's going to give me this error. A column vector Y was passed when a 1D array was expected. So basically, I sent it a column vector when it wanted an array. That's easily fixed by just using this ravel thing. It's included in the NumPy package, so it's already built in. Quick fix. Predict, just like we did earlier. And now remember, instead of using R squared for logistic regression, because we're predicting ones and zeros, we want it to be, is it correct? Is it not correct? We're going to look at the confusion matrix. So we need to import the metrics from scikit-learn. And we're going to create our confusion matrix by looking at metrics and calling confusion matrix and comparing Y test versus Y prediction. So it creates a little array, which is not very pretty. So I actually like the Seaborn option instead. We can take that matrix and make a heat map. So import Seaborn again. And that's much better. We can look at predicted labels and true labels and look at, okay, I predicted 0 and it was actually 0 4 times. I predicted 1 and it was really 1 0 times. But look here, I predicted 1. Oh, wait, sorry. I predicted 1 and it was actually 1 twice. This is how many I got wrong there, so that's good. But I predicted 0 and it was actually 1 once. So that's where I got it incorrect once, or the model did. On a data set the size of this, that's actually pretty good. If you look here at the classification report, you'll see our accuracy is 86%. And you see that by just going to accuracy, 86. Again, a data set of this size, that's pretty great. That's about as good as I'm going to get it for now. But we want a larger data set. So let's actually do a bigger example. I'm going to do it with this breast cancer data set. It is from the UCI machine learning repository. And what's nice is that they actually built this thing in where you can import it directly into Python. So you don't have to download anything. We're going to pip install it directly into our notebook. And then we're going to import it. And hopefully this works on your computer. Let me know if it doesn't. If it doesn't work, you can always go to this link and just download it as a CSV, and it should work. So I'm just going to show you the variables. So we have ID, which is a categorical variable, and it's just an ID, a diagnosis, which is our target variable. And then we have all these features. So radius, texture, perimeter, area, smoothness, compactness, concavity. So it's looking at these essentially masses and breast cancer. I believe is it ultrasounds? Yeah, digitized image of a fine needle aspirate of a breast mass. So it's taking this data and it's trying to say, can we predict if it's breast cancer or benign? Because if you don't know, a lot of breast masses are actually benign, but we need to make sure. What's nice about this is that because these are labeled as ID, target, and feature, they've built in this thing where we can say X is all of our features and Y is all of our targets. So that's something that's not included in data sets we bring in using a CSV. So a few quick things we're going to do. First, M is malignant and B is benign, but we actually want these to be zeros and ones. So I'm going to change this to say that if it's malignant, let's do a 1, and otherwise it's a 0. So you can use this in your homework and stuff, so make sure you're saving this code. Just a quick if else. You can ignore this type of warning. It's a setting with copy warning. It's just saying, hey, you're changing a value on a copy of a slice. It's not a big deal. And then we can continue like we have been. So split the data into training and testing sets. And I'm just going to show this so you can see what it looks like. So exactly like it has been, but just on a much larger data set. And now let's create our logistic regression model. And you'll notice I actually knew this was going to happen. I kind of built this in, but you get this convergence warning. So it failed to converge. Total number of iteration reached a limit. So this is telling me that I can increase the number of iterations or I can scale the data. So this is essentially saying something's going on with this data. Either you need to give us more time by increasing the number of iterations. So logistic regression has a built-in number of times it will try something, or you should scale the data. So if you look at this data, obviously the diagnosis is 0 and 1, but if you look at radius, texture, concavity, all of these are on different scales. And when you're looking at numerical models, the statistics of it, it's really difficult for a model to try to create an equation when all of these are on different scales. So we're actually going to scale this. And I put this down here too if you wanted to take another look. So see how these are double digits. These are very, very tiny numbers. Again, small. These are huge numbers. None of them are on the same scale in the same units. We want to normalize these. There are many ways to normalize and scale different variables. I'm going to use my favorite, which is min-max scaler. So if I do this, and then I show you. So what I did was import min-max scaler. I started it, I fitted my x variable, and then I transformed that into x scaled. And then what I did was sent x scaled and y instead of just x. So now when I show you xtrain, it changes what it looks like a bit. But now you see that it's on the scale of 0 to 1 instead of all of these different ones. So I personally like it. There's tons of different ways to do this. Some assume a normal distribution of all your variables, some don't. So just look into some of them and see which one. Min-max scaler is a nice general introduction to these. And from here, we can start making our model again. Let's predict, make our confusion matrix. And so remember, predict 1, it is a 1. So these are correct. These are correct. These are the only 2 we got wrong. And if you look into this a little bit more closely, this actually probably isn't that great, but we predicted no cancer and it was cancer twice. So not the best way to be incorrect. So if you start to look back into the actual reason we're creating these models, maybe not the best way to be incorrect, but it does show us that this model is way better than it was before. Our accuracy isn't, and by way better than it was before, I mean, it actually ran this time. And this is a better model than our CARS model. If you look at the accuracy, it's 98%. And these other scores, again, I'm not going to go into them this week, but you can see just by taking a glance at some of these other metrics, precision, recall, F1 score, you can see in general, we're doing a little bit better on the benign tumors. Malignant, it dips down a little bit. That's where we were wrong just on 2 of them. So there are other techniques to help boost those scores. So in general, as we wrap up this module, we covered 2 supervised learning techniques, linear and logistic regression. We discussed the implementation and evaluation of these models and began the process of interpreting them. So again, just started taking a few steps forward. We're going to continuously work on that. Next week, we're going to pick up with supervised learning 2, tree-based models. I will see you then. Have a good one. Bye. If I can pause. Sorry, it's going to keep going.